Thank you very much, ladies and gentlemen. Shall I begin by thanking the ICRP for making me a member of the committee and inviting me here, and to our host from the United Arab Emirates for a wonderful and friendly welcome to their lovely country. And I will begin straight away. You have seen this map or variants of this map. They always show the terrestrial part of the accident of Fukushima, but here we're going to talk about the marine part, because the radioisotopes that were released during the accident came in important quantities, which exceeds what was the effect of Chernobyl in the marine environment of that accident. And so, to set the scene, this is therefore the largest single accidental release of man-made radionuclides into the sea from civilian nuclear normal operation. The main radionuclides were iodine-131 and cesium-137, 10 to 16 becquerels of cesium discharged to the sea, the contamination dispersing into the Pacific with the winds and currents, but some of it in the local area, and some delayed inputs that have been exposed even recently. These therefore arose immediate interest, and very early there were initial estimates of the impact of on non-human biota. The initial calculations gave doses of the order of 0.2 to 5 grays per day. This was based on assuming maximum concentrations, and it was based on assuming an equilibrium. And by equilibrium, I'll mean that the activity in the biota is equal to the activity in the seawater multiplied by a constant concentration factor. And this, we immediately thought that there was opportunity to improve. Our hypothesis was that the activity in the marine biota would be below this maximum predicted by the concentration factor approach, because the turnover of the radionuclides by the biota is a process that works in combination with the discharge fluctuations. And therefore, those doses could have been estimated to be higher than they really were. This we had already seen in previous studies where I was working on the case of the Sellafield effluent, which discharged peak discharges of technetium under authorization, and those were also non-equilibrium situation, and in there we proved that there is indeed this delayed effect, which can only be calculated with dynamic models. So, very soon after the unfortunate accident in Fukushima happened, we did an initial study with what then was very limited data in order to assess the radiation doses to biota, including assessment direct from monitoring data from monitored biota samples, and with dynamic modeling allow us to predict concentration in biota in non-equilibrium condition. We used data from various sources, concentration in seawater and sediment from Mexton that began to be published, and have been summarized in Ken Bussler's 2011 paper, which conveniently put all this early data in his supplementary material. And we also look at some samples that, in our case, Greenpeace came to our institute with a collection of samples that we then analyzed and allowed us to make some initial calculations of the doses to the marine biota. The activities in the seawater can be seen in these graphs. These are measurements, and they showed us the different spikes of radioactivity that were coming into the water in the first months during the accident. This is the contrary to the typical nuclear power plant assessment of situation of equilibrium. So it was the case where we really had to try and see the differences between dynamic modeling and the old way to do an equilibrium approach to calculate the transfer of the activity to the marine biota from the seawater. These data can be put in a time graph, and the first thing that you can see, apart of the sparsity of the sediment data, which were not very many, and these are the red dots, is that the activity concentration of radionuclides in the water decreased after peaking at a certain exponential rate, whereas in the sediments, the radionuclide concentrations showed no such pattern, indicating a retention in the radionuclides due to absorption, due probably to the influx of biogenic particles that scavenge the radionuclides from the water column and bring them to the sea bed. And as of May 2011, they were about 10 to the power of 5 becquerels per kilogram in the seaweed. And there was cesium 137 and 134 in virtually identical proportions. So to do those assessments for, I repeat, not for the human, but for the non-human biota, there are three ways to do this, and I won't have time to go through the maths. The first way is you take the activity concentrations in the samples of fish, seaweed, etc., and use those directly and multiply by the relevant dose conversion factors and dosimetry calculations to get the total dose, which is the sum of the internal and external exposure. If you have activity in water, but you don't have biota, which is typical of the early phase of a problem when people hasn't had time to go and collect, you have to do some calculation. You either multiply by a concentration factor to get an idea of the transfer to the biota, but I've already said that this is not the right thing to do in a situation like the one we are dealing with here. Or you use a biokinetic model, which in its most simple form expressed here is an exchange between the water and the biological compartment mediated by first-order kinetic equations, which are with the key parameter is the biological half-life of elimination of the radionuclide. This can be made more complicated, and we have models with 2 and 3 biological half-lives and organs and all this, but this we didn't apply here. The doses to the monitored biota we calculated. We calculated that the exposure in seaweed was the dominant one. So seaweed, the marine plants were the most exposed organisms, principally to the iodine-131 in the very early moments of the accident. The internal dose rates of these samples that we had were less than 13 micrograms per hour of iodine and less than 0.19 micrograms per hour of radiocesium, and that the external dose rates were typically between 4 and 10,000 times lower, depending on the station and what was in the sediments, etc. So in principle, the internal dose component in these very early days is what dominated the total dose to the non-human biota. And that is a significant reduction to the early calculations that had been done, assuming without the benefit of having biota samples directly to do a calculation of the dose. But as I said, in the early first, I remember, I think 20 or so, 30 days following the accident, there was no data on biota that we could find. We only had seawater, so we applied our dynamic model. And this picture here shows the importance of dynamic modeling as it gives results for this situation. And it also shows two things. Without going into details, you see two types of curve. The smooth curve is the curve of the dynamically predicted activity in the biota calculated from water using biokinetic modeling. And the more pointy dotted curve is the result of doing assumption of equilibrium. And what you see is that when the concentrations are increasing in the environment, the equilibrium assumption overestimates. And when the concentrations are falling, the equilibrium assumption overestimates in relation to the dynamic modeling. And this is because the biota are acting as a capacitor in a circuit. This is almost like if you do electronics, a low-pass sort of circuit where there is a delayed response and accumulation. So it's not terribly surprising. The dynamic dose modeling results, which are useful because it tells you something at the very, very beginning when we don't have monitoring data, show the iodine doses of the order of 20 to 25 milligrams per hour in macroalgae and 15 to 60 micrograms per hour in other species, and in the immediate vicinity of the Daiichi power station, and 30 to 40 times lower in the outer locations in the nearby coast. Most exposed organisms confirmed to be the macroalgae receiving an iodine from Daiichi outlets, but that was a transient situation because this iodine decayed with an 8-day half-life, so it's by now all disappeared. Organisms outside of the nuclear power station immediate vicinity, 4 micrograms per hour radiocesium, and still 750 micrograms per hour of radioiodine in the first month. And then the internal dose rate still dominates over external because the sediments haven't had time yet to absorb this radioactivity and give an external dose to the benthic organisms. Cumulative doses could be calculated as 6.5 grams for macroalgae, 2-3 orders of magnitude lower for fish, crustaceans, and mollusks. Just to put some numbers. And this slide here shows you the difference between applying the dynamic model to calculate doses, applying applying concentration factor to calculate the transfer from which you calculate the doses, or applying dynamic modeling to calculate the transfer from which you again calculate the doses, or from calculating the doses directly in using the biota and just multiplying by those factors. And the key important fact is that there is a 2 order of magnitude difference between the dynamic modeling estimation of transfer and the estimation using equilibrium. So clearly dynamic modeling, which originally was considered to be perhaps not necessary for assessment, here it shows as a useful tool to avoid over-assessing the dosimetric situation. This bit here is going to be extremely short. I was involved in the on-scale assessment, doing a large part of the marine assessment. I would have loved to be here telling you all about it, but I must bite my tongue as hard as I can because this report has been delayed, and tomorrow Carl Magnus will present it to the United Nations, so I really can't go into details here, and I hope you will forgive me for this. But the OnScare, you should know that it has done an assessment with 60 international experts from 18 countries that they have put together for expert groups, measurements, source term, dose assessment, and risk analysis, that Japan provided an extensive data set, and that with this, an interim report was issued, which says very little about the biota, introduced in 2012. And the next report is to the committee of the 68th session and the General Assembly, which will be issued on Friday, and a very completely detailed report with full assessment in larger scientific appendices, I think is due in a couple of months from now. But the key, this slide is misleading, it's not their finding, so what I can say is that the assessment was performed with an extensive data set of over 500 sediments, 6,000 seawater, 5,000 biota dose points, source organisms where the water plants. In general, the exposures are considered too low for observable acute effects, and this is based on current dose effects benchmarks, and I'm afraid that the full detail will have to come later, although I would have liked it to come now. Then, to continue our involvement in this story, we looked at the current situation a bit more in detail, because, of course, the issue has kept hitting the news periodically. And late last year, there was this paper again by Ken Busler, Fukushima fish may be inedible for a decade, editorial in the press, because they had found fish which had specific activities, radiocesium exceeding 10,000 becquerels per kilo, and this is exceeding the 100 becquerels per kilo of the Japanese seafood limit. So these things we have been hearing along the press, and in various places, and they mean that we have to continue investigating the situation. TEPCO produced a report, result of radioactive nuclide analysis around Fukushima nuclear power station, indicating that the seawater contamination had decreased from 100,000 becquerels per cubic meter to a few becquerels per cubic meter, but that sediment contamination had not changed significantly, and that again reflects the ability of sediments to retain some of the radiocesium due to the absorption into its surface and perhaps delayed inputs that have been occurring. So what are we to make of these high levels in fish? And the DEPCO report, I think, gave activities as high as 10 to the 5 becquerels per kilo in 1 or 2 greenling fish that they found in the very port, exactly inside of the port of the Fukushima, inside of the nets. So what are we to make of this? We have a problem or not? When you calculate the doses, you get 20 to 80 micrograms per hour, which is in that region where you still don't expect large effects or to see effects affecting whole populations. But it's in that little gray area below that. And how many of these fish have these high activities? Well, what I did is something very simple. I put it in a distribution and I obtained the typical log normal distribution. And I found out that the fish that have the highest radioactivity are the ones at the very top of the log normal distribution. In other words, they are not that representative of what's happening at the species level in this area. And so you can calculate a median of 1.38 micrograms per hour for the fish in the area, and 95% of the results below 50 micrograms per hour. And so you have to always put things in context and not take the most contaminated sample and say all the fish are receiving such and such levels of radiation. So, but we need to keep updating the dose assessment, and the highest doses seem to still be below the level at which you expect important effects in the population level. But, and from our histogram analysis, it's unlikely that the elevated concentrations in individual specimens are happening all across the board. However, these are not negligible activities, and therefore, although we are not in a threat, in an ecological threat at population level, this continues to be needed to be investigated as part of the ongoing effort of marine radioecology in this field. So, the main findings, the doses calculated in the various studies are generally below the amounts necessary to cause a measure of Western populations, except perhaps at the very early stages with iodine in microalgae in the very close vicinity of the plant, but not further away. And these levels, however, cannot just be called negligible. They require further study. And we have various these I will skip because I don't have time, but if you want to know about the uncertainties of the assessment, you can ask it as a question or maybe for the discussion. But these studies have limitations. Limitations like you cannot account for all the radionuclides present, you have to use the measurements you have. You cannot include exposures from sediment when modeling external doses if you don't have sediment measurements unless you have dispersion modeling calculations. You have, many times when you have these monitoring results, a lack of match between the locations of water, sediments, and biota, which make the external exposure assessment difficult. However, the broader on-scale study is comprehensive, really comprehensive, and it has much more data with which to iron out some of these problems. But one of the lessons is we should have a publicly accessible extended database of all the results so that people could continue adding to it and doing more calculations and assessment calculations on this. The effects predictions, I'm not an effects expert, in case you want to know, but I know that there are limitations on the effects predictions. For example, moment, I think I jumped one. Limited effects data, yeah. Application of benchmarks that are for acute or for chronic in an acute or chronic situation, problems with what happens to the most exposed organisms as opposite to the average organisms, what is the alterations possible to a population level, you cannot calculate so easily, and you have to put all these things in good context. There is a need to characterize local hotspot locations, which has not been perhaps fully done yet. Our understanding of the biological impacts of radiation is still limited and is at present based largely upon limited high exposure data collected under controlled laboratory conditions. Biota have variability on their radiosensitivity interspecies, and they might react according to complex interactions, including radiation and toxic and other substances. And there are no reported observations of such effects in Fukushima environment that have been categorically established. And so there is a degree of learning that we need to do in doing this work. And now to the last 3 slides. There are some future issues. Recently we've heard about the leakage of the tanks, that potential leakage in water tanks in Fukushima that could go via groundwater into the sea and produce potentially local hotspots of higher concentration that could persist as secondary sources. This is to be investigated. The biota in some sites might reflect this. And you probably continue to find fish specimens with slightly higher activities than the remaining ones that will hit the periodicals, the press, etc., for years to come. Meanwhile, the dispersion through water continues, and there is a continued settling of radionuclides in the sea floor due to scavenging by biogenic particles and absorption. Investigations must continue. There is a need to conduct more field work, more reliable model predictions, conduct long-term effect studies, and revisit current assessments in future, and assess effects at the population level. I predict that for the next 20 years, this will remain an interest in the community. And finally, let's not forget that the impact of the overall environment, including the abiotic part of it, was beyond the scope of these studies. And we should acknowledge that a dose-based assessment implies a biocentric paradigm of sort. and that radiation dose cannot capture by itself the impacts to the actual value that mankind assigns to an environment. And this is something that we should not forget when we're communicating with the public. Small doses of 2 micrograys per hour, for a scientist, that's a small number, but this is 10 to 4 becquerels per kilo in a fish. And this, using a concentration factor, can be 100,000 becquerels per kilo in seawater. And this is comparable to studies to the radioactive levels in Sellafield, in the vicinity of the Sellafield environment at the 1970s when the discharges were at their maximum peak. So if that was of interest then, it should surely be of interest now. And the environment has a value that is publicly perceived as being affected, and we as scientists, we will always have to answer these questions in the best way we can. And so when we start saying negligible and insignificant and words like this, they don't go very well because they don't communicate this aspect of it. The IAEA pioneered many things, including the report on applicability of the radiation protection framework to the abiotic environment, which is an issue under debate. And with this, I hope I gave a flavor of the picture in the absence of the on-scale assessment. You just need to wait one more day. And I thank you very much for your attention and the opportunity to be here with you today. Thank you.